Today, I'm going to be running a bulk EBSD map on this enormous Tie 6.4 sample. It is 8 by 6 centimeters, and I'm going to run it on the new Thermo Fisher Apreo SEM with very large stage. And you can see that it's so large that I'm actually using 4 stubs with a ton of super glue on just to make sure it doesn't fall off in the middle of the scan, because I am absolutely terrified of that. This is the Apreo stage holder. It's quite a large one. It's built for large stage EBSD. And so what I did is I added the 4 stubs into the slots before I actually attached them to the sample, so I knew they would fit properly. So yeah, let's give it a go. Okay, sample is now in the microscope. The vacuum, the chamber pressure is now below 8 times 10 to the minus 5 millibars, so we're good to go. So that's the sample in the chamber. It is absolutely enormous and absolutely terrifying. I already took a navigation cam image so I can scoot around the sample should I need to. It's quite nice because you can actually see the reflection of the camera and the sample's so absolutely enormous. Right, so this is a titanium 6, aluminium 4, vanadium in weight percent titanium alloy. It has been deformed and not annealed, so the ideal situation would be for any sort of decent EBSD map, you don't want it deformed because then you can go faster, get better indexing. For this, I'm going to have to be a bit careful about it. However, as I'll get to later, I'm going to max out the amount of pixels we can take in this map to make it as big as we can actually make it. And to do that, we need to be going pretty fast. So I think the minimum speed we can run it at is 300 hertz. And to do that, we need A, high current, B, and a CMOS detector, which we have. We have one of Oxford Instruments Symmetry 2 EBSD detectors. I have to use a pretty high current, so I'm going to use 51 nanoamps, and I'm running at 20 kV. Beam on. A lot of current. Right. So the high current brings out the OPS on the surface. It's very hard to clean this material anyway to get it all off, but it looks much worse than it is because of the high current. Already we've got a scratch on it, but it's been prepared painstakingly by hand, so it's not surprising there'd be a few scratches on it. So let's just get set up. Just align the source. I'm going to focus on something small and circular to make life easier. You can already see some of the microstructure in the material. So again, the high current. Stig. Not going to get a great focus on this. So again, we're looking at something that's about a micron in size, and we're throwing down a lot of current. Beam wobble, might come out a bit on this. A little bit in Y. Might be actually better to do this in something larger. Let's try U. Yeah, so we need to pop in the Y. Okay, that's about as good as it gets on this microscope. The optics on this are really excellent, actually. And you can throw down 400 nanoamps of current. Yeah, 0.41 microamps of current. You could melt this material if you left the beam on long enough. That's a lie, you couldn't. Might just move this microphone across. Okay, I'm going to link the working distance now for now, so we know where we are. I think so. I'm not going to be able to get to a full 70-degree tilt as you normally would, because the sample is absolutely massive. The Apreo is designed for large samples, so the angle of the pole piece is actually 60 degrees. So you can tilt to 60 degrees and know that your sample's never going to hit it. But you don't get great indexing at tilts that low, so I'm going to try 65-degree tilt. And normally I would bring the sample at working distance about 22 millimeters from the pole piece, because I know you can tilt the stage and get pretty decent setup like that, but I'm a bit concerned it's going to be too high, so I'm going to move it to an even 30 and then try tilting to 65 there. Hovering over the stop button just in case. Okay, so we're good. The other nice function of this this microscope is we can actually zoom in on certain areas, so we can really see how close we are when we start moving it around. So if I now, let's just take that zoom off for a minute. If I now start scooting up the sample, let's see if we can get to the bottom of it before we hit the pole piece. Oh, it's so close. I think we're going to be fine. Yeah, we're good. I mean, it's a slight angle to the sample here, but you can see that we've got a decent clearance. We're okay. We're not going to break anything. Just going to check. I'm going to use field width of about. I'm going to try 1.38 millimeters across for a frame. I think we're good there. Right. So what I need to do now is on this software, you can store your positions. So I'm going to store positions of all 4 corners of the sample before I bring in the EBSD camera. But as you might expect from a sample this large, it is not flat. So what I'm going to try and do, and hope this works okay, is I'm going to keep the focus the same across the entire sample, but change the Z height. That's the direction like this, moving towards the pole piece from the stage, and bring each corner of the sample into focus, or roughly into focus. And then Aztec software that I'll be using later should interpolate Z distances that correspond to the focal plane in each of the samples, each of the sample corners. But the question is, if the change in sample height between frames is too much, then you're going to get massive stitching errors. So that's one thing we need to work out. It's also rounded at the corner, that's not helpful. So you'd expect, you can already see that this sample is curved at this corner, so I'm going to come in quite a bit. We can lose the corners, that's fine. Right, so this one, I can just focus, no problem. I'll do stig again, but I won't change the stig for the rest of the sample. So pretty good for that. I'll just focus on, see if we can get a bit better focus on this. Right. So now what I'm going to do is I'm going to unlink Z to my working distance. So we're now reading Z measurements going upwards. So the stage completely down would be 0. Right, so I can store this point. No, I can't. I need to actually move to where I'm going. So I'll try and get a border around the sample as well. We want to be flashy, don't we? So I think this is approximately the highest point. So I'm going to go a bit further up. So that is 39, no, that is 9.57. So I'm just going to find this edge of the sample, go right out, and go to 9.57. Okay, first point added. I'm just going to make a note of that Y coordinate because I'm going to move back to that when I find the other edge. So we get a map with a straight line. 6. Okay. Now I have to go all the way across. Maybe I'll do this bottom corner first. God, it's massive. I'm a bit worried we're going to hit the bottom of the chamber. No, we won't, because the stage will hit first, because the stage is larger than the sample. Can't see where it's going though. That is coming through. You can still see that, yeah. Oh God. This is the corner. And we finally got the corner. Right. So let's find something to focus on. There's a lot of stuff around here. It's surprisingly in focus. Well done on the sample prep. Jeez, that is incredible. Let's try one. Let's try this. I mean, that's pretty good already. I've adjusted a little bit, so I'm just going to move in Z. So it's going to see the image move. That's the wrong way. But it's not going to be much better than that. Now I'm going to leave it there. Absolutely incredible. Nice and flat, lovely. And across 8 centimeters, that's unreal. Well, this is 6 on this edge. Right. Let's go down again. I'm going to make a note of that as well. So this is Y minus 47. Okay. So find the edge again. I'll probably read off the other one, the X value from the other one, I think. That was minus 41.65. Now, yeah, not the exact. And then we're going down to 47.12. Cool. Point 2, saved. Now I've moved a bit in Z, so I am going to scoot right back up again to the top of the sample, just to make sure that that change in Z doesn't bring us anywhere near the pole piece before I start whipping between positions. I'm not using the NavCam image because this is no longer relevant. This screen here is what we're looking at and where it thinks we are on the sample. So we're obviously not there anymore. So I'm not going to double click that. Because it will move quickly and it will smash everything. And I'll be in a lot of trouble. God, this takes absolutely forever going from one side to the other. God. Okay, we're still nowhere near. We're fine. So now if I go move to this first point, it shouldn't move far in X and Y, and the Z coordinate shouldn't change much. But after I click this go to button, it's going to change to stop, so I'm going to be hovering over that just in case. And we're good. And then let's go down to the other one. That's the less scary one. This is the scary one, going towards the pole piece. Oh, that's seriously stressful. Okay, we're safe. Let's move on to find the other side of the sample now. We'll probably cut some time off by putting 0 in the X coordinate. It's safe to move in X. And then I'm going to scoot across manually for the rest of it because I'm too scared of banging into something. And also, the further we move in this frame, the harder it is to see where it's going. And so the sample's moving towards the door now. I have serious concerns that it's going to break it. I'm sure it's fine. And I don't need to worry about it. Okay, next corner. Let's see how our focus is like. Again, it's pretty spot on. Oh man, such a good job on the sample prep. Well, yeah, I mean, the only way you're going to get the whole sample get a perfect polish on a sample this big is by using one of those machines. But by hand, phenomenal job. Let's get in the wrong way. No, right first time. There's plenty of me to sort of focus on as this thing moves. Okay, that looks pretty good. Yeah, nice. Right. So now I'm going to read off that Y coordinate I had before. Or let's get the X one down first. We want to go right across. So this is X equals 36.86. Okay. And then we want to go to Y 9.56. We're gonna index a lot of negative space, but it'd be nice to get a border on it, just so everyone knows we've done the whole sample. Okay. So let's add that. So now if I go between 1 and 3, it should move only in Y. Who says? Oh. Absolutely horrifying. I'm not going to sleep tonight. Right, well, I've got the bottom Y coordinate, but I'm not going to just tap it in and go. That's far too risky. I'm going to go bit by bit again. Although it is a long way to move manually. Oh, absolutely ridiculous. I'm doing this on a Friday afternoon as well. It seems like a stressful thing to do when I should just be at the pub. Oh man. Actually, I probably will need a drink after this. Okay. Right, we're at the bottom. Bottom of sample is minus 47.12. So let's go further. Okay, it's about right. Oh, I hate when it does that. Button sticks down and it moves you all over wherever you move the mouse rather than moving bit by bit. Okay, close enough. Next is minus 36.86. Close enough. Oh, I didn't check the focus. I'm sure it's probably fine, but you know, we'll do it anyway. Okay. So this way, I think. Yes. Wow, that's pretty good. I think it's going to get better. Maybe a bit. Okay. All right. Down we go again. So we're on Y is minus 47.12. Okay. And X is 36.86. Okay. Add. Right. Now I'm going between 3 and 4. Jesus Christ. Right. One last check. Let's go around all 4. Lovely. Just keeping an eye on the edge of the sample with each of these on the secondary electron image. So I can see that I'm not cutting off any edges. We go to 4, we can see that, yeah, just going down the side of the sample. 3 should go up. Keeping one side in view, good. And then this one back to the start, and it should eventually come into frame. Beautiful. Right. So now we need to bring an EBSD camera, but the camera's going to come in this side, and this is the safest position that the sample can be from the camera because it's furthest away. So what I'm going to do is I'm going to move the sample back down to one of the bottom points. Oh, wrong one. I think it's 4. Yeah. So this is going to be the closest it's going to get to the camera when it's down here. Right. So I'm on a separate PC with Aztec. So I'll just flick across. Okay. Now, yeah, just quickly. So I've named it the Beast, of course. I'm looking for hexagonal and titanium cubic. Specimen geometry, I don't change the coordinate system because it just confuses things later. We don't have a pre-tip holder, and they're just your phases. So let me go to hit in. So I'll come back to the camera screen. The symmetry is moving really quickly, but they usually have a soft stop in a safe position, so you can bring it in halfway in very quickly. And then the second step is the frightening bit. So we're going in really slowly now, and I'm keeping one eye on that on the sample. So it actually looks like we're miles away, but I think that's a little deceptive. And there's also the fact that the symmetry detectors are able to change their elevation like this, so we can better detect the patterns. So I'm going to stop it there for now, because the main issue is the patterns at the moment are going to be coming off the bottom of the camera because we're at such a low working distance. So if I now move back into the sample center so we can actually get some patterns on the material. It's 1.38 is my working distance. Okay. Just going to collect a quick image to tell the software what magnification we're at. Okay. So I'm going to go speed 2 because we need to go relatively fast. We'll change the exposure time and everything else later. For now, I just want to position the patterns. So yeah, you're barely getting anything at the moment. You can see they're all just right off the bottom of the camera. So what I'm going to do is use this elevation function to shift the camera a millimeter down at a time. We can still bring the camera in further, but we need to be confident that we've got our elevation correct first. So 1 mil at a time. I know it's going to be at least -7. So that's -4, -5. This green spot is showing us where it thinks the center of the patterns are. So we're still miles off the bottom of the pattern center. But I'm keeping a careful eye on the detector because we don't want it going anywhere near our sample. I actually don't know how far this goes down. -9, -10. -11. -12. We're about center now. I'm happy with that. It's never going to be perfect under these conditions. So we did the elevation. Okay. Right, I've just had to jump back because I forgot to change the screens. Great job. So I've changed the elevation of the camera to -12 mil. I think that's just moving down laterally like that. So now we've got our pattern centers in the center of the image. So we've got frame time of 0.3 milliseconds at the moment. Now I worked out from this mapping calculator that was done by Jack Donoghue that the minimum acquisition speed to fit in the time allotted, so I've got about 70 hours or so, it's about 300 hertz. That's the minimum we can go. And really, because we've got a deformed sample, we want to be maxing that out. It's not worth, we're going to have problems with moving working distances and everything else. The camera's a bit further out, so the longer the exposure time, the better on this. But even under these settings, we're going pretty fast. So I'm going to, if I change this to 1 millisecond, we've got, you know, some beautiful, strong patterns here. I mean, if you wanted to, we could take this. I've got 2 frame averaging on here as well. We could take it off and bring it down to 0.2 millisecond exposure, and we're still getting patterns. And then we'll still be indexing at over 3,500 hertz. But we're not trying to do the fastest map possible. We're trying to get the best indexing. So I'm going to take the frame time to 1 millisecond, and I'm going to put 2 frame averaging on, which brings us to 493 hertz. As for solving the patterns, I've stretched out the area to fit around the entire pattern. Under this setting, we've got a number of bands. I've chosen 10. I find that with titanium, if you go less, you get more problems with phase overlap from the alpha and beta phases. Because of the Berger's orientation relationship. So I've stuck with that. Off resolution, I don't think we need to worry about this too much. Going up to 100 is excessive. I'm going to put it at 60. For those of you who aren't aware, Hoff resolution is just, Hoff transformation is just, it takes the EBSD patterns that go across like this, these bands, and it takes the gradient and the lateral shift and takes those 2 numbers and plots them on a new graph. And then the band contrast comes out of these like contrast patterns here, these sort of butterfly patterns. And you can see the arrow going across on the diagram there. Not particularly great because I'm streaming this from one computer to another, but you get the idea. And the Hoff resolution just changes the resolution of this image, so it allows the pattern software to work a bit better. I'm going to go with 60 because I know that's a good place to start. I've noticed actually that we've got some spots on the screen there, so I'm actually going to go back. I've got the auto background on so we can better see the patterns, but I'm going to add a static background as well just to collect these extra spots. So that's now cleaned up. Just checking the camera, it's not picked up any extra EBSD patterns that it's going to overlay, so we're good to go. And I'll probably refine around a good pattern just to give the software some help. I mean, that's gone up now, but yeah. We're getting good indexing. That's the important bit. Okay. So I'm going to maximize the frame size. Still good on the, it's not moved, it's not gone anywhere, but it's worth checking just in case. I calculated with the mapping calculator that our step size needs to be 10 microns, so to not go over the limit. I mean, I've set the limit here as 48 megapixels when it's the 64 limit. So we're well below the limit, just in case the map I end up doing is a bit bigger than that, because I've manually entered the size, you see. Right, so we're going 10 microns. What I might do as well, just because we're doing such a big sample, it'd be interesting to see. I'm going to put on EDS as well. At the moment, the detector's out, and we've got dead time's about 30%. Normally, you want between 25 and 50. In an ideal world, you'd have the camera all the way in, but the dead time will go through the roof for that, and it will just, you know, fry the detector probably. So we can only put it in partially, which is going to cause problems as it is. But I'm going to bring it in until we get a bit higher up. So I'm just watching the dead time climb now. Oh, I managed to get it all the way in and it didn't change. Why didn't that change? Interesting. Well, we'll keep an eye on that, but just show the screen there. There's your EDS detector, hiding behind the secondary electron detector there, almost beautifully sort of arranging it. But we'll keep an eye on that and see how it goes. Usually at a 51 nanoamp current, the dead time should go through the roof, but it might be because the sample is so low at the moment. So I'll check it when we move the sample up in a bit. Okay, so that's on 10 micron step size. We've got our points saved already. So we go new area, we go quadrilateral. So I'm going to input 4 points just to show you that. Okay. So automate, new area, quadrilateral, 4 points. Here we go. So now we move to our first point. And we know by, because we went to the most dangerous position first with the EBSD camera, we should be able to move right to the bottom of the sample with no worries about going anywhere near the detector. So we're absolutely fine on that front. But just in case, I'm going to double check that we have this proximity detector on, so that if anything does come near the EBSD camera, it's going to retract the second it senses anything. So we're safe on a number of fronts. So we go to position 1. If it goes. Jesus Christ. Okay. And we accept that. My hard drive is almost full. Great. Okay. Position 2. Oh my God. What's this? Go away. Okay, position 2. Accept. Position 3. Oof. Accept. Position 4. Oh my God, it's horrible. Okay, accept. Great. So now we have our all 4 points, and I'm just going to check them all once more, but now controlling it from Aztec, so that I can leave it to run over the weekend and know that it's not going to go anywhere outside of these 4 defined points. So I hit go to on point 1, and then it should move to exactly the same spot it did before. No reason it wouldn't, but it's good to double check just to be happy. Second point. Third point. And then fourth point. Lovely. So we're good. And that has calculated that we have 4,158 fields, which is approximately what our calculator told us, 4,214. So we know we've got the right size. We know that it should run the correct map, and we know that it should still be able to stitch at the end of it because it's below the megapixel limit. The last thing I'm going to check is just that EDS counter. So if we go to one of the higher points, nope, not that one. And this one. And I'm just going to, I'm just going to move back onto the sample. Keeping that magnification constant so I don't confuse Aztec. See now, look, our dead time is 70%. I knew it. So we still need to pull that out. So I'm going to partially pull that out. You see, that's interesting. Oh, I know why that's done that. It's because I've got with the infrared camera on, it emits radiation and it gets picked up by the detector. So that's now down to 30%. Okay, so I'm going to put it in again, backwards and forwards.
Okay, so actually it's fine. You can even go up, take it up some. Right, I'm going to accept this map. I'm happy with that. But on these settings now, you can just change the process time. Swap my dead time to about 40% or so. Okay, good. One last thing to just check, see how we're doing. I'm just going to run one frame individually without running this map, just to see what our indexing is like. Pretty good. We're at the edge of the sample. We've got some dirt on the surface here, but it's still running at 83% indexing. I'm happy with that. Probably don't need to collect all these signals actually. It's got Chrome and Molly running. That's not in the sample. Just turn those off, probably on predefined. Yeah, predefined. So we'll clear that. Clear the Molly. Iron, yeah. Vanadium, titanium, yeah. Aluminium, probably good. I usually have carbon and oxygen on just in case. Normally the signals don't really help you much, but it's fine. Maybe just shift across. And just check one more frame. Okay, looking good. So you're not seeing a lot there, but your step size is 10 microns. The whole point is in these samples, because I think this one's forged, you get texture bands on a millimeter scale throughout the sample. So when we do the large scale, you should be able to see how it changes throughout the material. There's probably a long string of bands like this. Okay, so we're good to go. It's pounding a little bit, kind of terrified. Normally I turn this proximity detector off because it does interfere with the pattern somewhat. Normally gives you a little bit of misindexing, but I'm going to leave it on because the sample's massive and this whole thing terrifies me. That's all good, that's on. And the last thing I'm going to do is I'm going to tell it to turn beam off at the end of the run so that the electron beam isn't left running for days on end. And then we hit run. Save it. You can see how tense I am. Go. You can hear it still moving, but it has to pause this screen in the bottom right, so I can't see what it's doing and I can't keep an eye on it. Horrifying. That's the EDS. We don't care about that for now. This is the IPF. So this is just going to be our boundary. The first, maybe, I don't know, however many frames it is going up that one side, probably going to be just white noise or black, whatever. But if I stay here long enough to actually get a decent amount of see a decent amount of indexing on the screen, I'll put it at the end of this video. If not, I'll try and post a finished map again, either at the end of the video or I'll post it online somewhere. It might, because the sample's a bit sensitive, so it might not be able to put the data up straight away. It might go out in the publication, at which point I'll link the publication instead. Right, so it's been running for about, I don't know, like 15 minutes or something. And you can see we're starting to get the side of the sample now. This bit's a bit rubbish because that's right at the edge. But if you look where we are now, it's indexing pretty damn well. I mean, it's easily 85% at the moment. And it's going nice and quick without any problems, or I can't hear the sample scratching around in the chamber. So no disasters, it looks safe. Yes.